So I gave you these problems the other day. Maybe you still have them. Let's have a look at these, but I will give kind of a little bit of an introduction to this. The idea is this, a stress concentration. I think I'll go down to this page, the bottom down here. What is a stress concentration? It's kind of a cool idea. Unfortunately, the using of it is pretty straightforward, but I want to give you some sense of conceptual understanding of it. Maybe you know this. Here's a river with the water flowing in this direction, and here's a rock out in the middle. Where do the fish hang out? Yeah, does it make sense by virtue of the fact that there's a rock in the middle of it? You know, this current over here just kind of heads on down the river, but the stuff that's right here has to kind of hit the rock and go around it. And this hits the rock and goes around it, and this hits the rock and goes around it. And then when it gets to the other side, it does the same thing. So the fish actually hang out. Uh-oh, here's a fish. That's a terrible fish. That's an infinity sign. That's why you don't record yourself. There we go. The fish hang out basically right here because they're getting a concentration of food right there. Does that make sense? They're basically getting all the food that would have went down the rock, and they're getting it around the edges. So in effect, they're actually kind of getting all of this food that would have been right here. All of that food that would have been in that section right there is all coming right to that spot right there. And so it's concentrating it. In the case of a house, how does this work? You have a house. Awesome. Actually, I think I'll draw this slightly differently. There's a house. Now, you can probably appreciate that all of this part of the roof kind of sits evenly, and I've showed you this a little bit in statics, there's a rafter every 2 feet. So there's just a bunch of weight all the way along that part of the house. Well, what happens if you come in here then and you put some monstrous window in it? You stick a window in there? The answer is no, because glass is not going to hold weight, and you've now made it so that there's sort of a spot that can't hold weight. So how's that supposed to be held up? How's that window going to be held up then? What happens inside of a house? Do you know this? So here's your window. You basically have to throw a beam over the top of that window so that all of that load coming in from the roof sits on that beam. And of course, in order for that beam to not just rest on the glass, then you've got to kind of put a post over on this side. So that's called a post and beam structure. Does it make sense then that that does the exact same thing the rock just did? It takes all that force up there, and what does it do to it? It moves it, it concentrates it. Basically, this force over here is going to kind of flow, you might say. Basically, everything that's on that half of the building is going to flow over there. So it's going to concentrate a whole bunch of that roof weight just in one spot. And underneath the house, sometimes I've got to put kind of a larger footing underneath there to carry that, because there's so much weight concentrated at that point. And so really, this is just about the fact that stress gets concentrated when there's kind of an obstacle or something like that. A window is an obstacle. In this case, the roof doesn't know there's a window, it just knows there's a beam. But that's what you do for a door or a window. Anytime there's a hole, and I mentioned this window over here, notice that's a gigantic window. It goes all the way across this building. And so there must be a huge beam because it's so huge. And there's no structural support here. This is just a frame for this glass. That's literally like one giant long piece of glass. So assuming the roof up there is actually resting on this, which by the way, it doesn't have to be. The roof could be going this direction. And so the roof is actually resting on the sides where the roof comes down. And so maybe there isn't that much weight here. So it kind of depends on how the roof's designed. I know this roof is flat, so I'm sure it has a bunch of weight on it. You can see in that flat building over there, and all the flat buildings you can see, the roof goes all the way around it. So it's kind of sitting everywhere, if you will. So there's some things to think about there. But does that concept that you're taking the stress that would have been evenly distributed and you're concentrating it in one spot? Well, take a look at this problem then. Do you see the same thing here? In other words, here's this axial force. Again, I'm anxious that that word means something to you. Axial meaning lengthwise. And do you see how there's a couple of P's for pounds there? It should say F for force, I suppose, but P for pounds, and it's pulling on that thing axially. Well, does it make sense what's going to happen around that hole right there? So there's two things to consider here. One of them is the hole and one of them is the fillet. We're going to look at kind of both of those. But that's going to kind of concentrate that. So think about the force that's kind of right here. You know, that part of the force that's right there, does it make sense? It's going to have to kind of flow around the hole, if you will, and the hole is going to cause that to kind of concentrate in the same exact way. And so a hole represents a place where there's concentration. So if you come over here and say, oh, there's 100 pounds right there. Well, now because of the hole, you can't think of it as just, oh, it's spread evenly. I'll just take that 100 pounds. Remember, stress was the force divided by the area. I can't just take that 100 pounds and divide by the area now, because all of a sudden the area is all screwed up. Does that make sense? The area over here is fine, but then what happens over here? Notice as well, I mean, the thickness is still, notice right here, we're told the thickness is only 1/8 of an inch, 0.125 inches is how thick this piece is. But over here, where that particular hole is, that kind of concentrates it. And do you notice the same thing happens over here? So we've got a hole. You notice it necks down over there. There's another spot, and I don't think this is in your book, but that thing is called a fillet. Anything that's rounded off, is called a fillet. This right here on the corner of the desk, all of these are fillets. They're rounding a corner off. It's a super common thing to do. It keeps it from breaking. If you bump into it, it'd chip off, and also it allows this plastic edge to go around it and make the corner, which it wouldn't want to do if it was perfectly straight. So when you're going to transfer, notice they took this shape and said, hey, let's have this thing be 1.875 inches tall. And then when they got over here, they went, nah, let's take it down to 1 1/4. Well, how do you transition that? A lot of times that'll be rounded off instead of squared off. And so if it's rounded off like that, it's called a fillet. But that's a nice way to transition it so that it's sort of smoothly. Well, do you see the same thing happening there? I mean, if you think of the same thing I was discussing, kind of the idea of flow. If I've got the flow force coming here, isn't that force going to have to kind of turn and work its way down here? So essentially, isn't there going to be a concentration right there? Notice these forces don't notice that. They don't know anything changed, right? But all of these forces up here, they're going to have to all flow together and concentrate. So stress concentration, there's going to be concentrations where a shape necks down like that to something smaller, or if there's a hole in the way. You see the basic logic to that? And so let's just take one quick look at your note sheet for this section. Notice the stress concentration is kind of this K number. And basically what that is like a constant that basically allows us to ramp it up. Notice if you were to take this formula right here and figure out what that maximum was, all you'd have to do is multiply the average, the normal sigma, the normal stress you would have had, and then you just multiply it by K, which kind of bumps it up. So does it make sense? K is always going to be more than 1. So it might be like 1.2, it's 20% more, it's 30% more. K will be 1.2, 1.3. And in order to figure out, oh, what's the actual stress? What's that maximum stress? Remember, I say maximum because in the middle of those things, you don't notice it. That was the wrong one. This one? Yeah. This force over here doesn't notice. That's going to be the same old stress you always had. But these are going to notice, right? Like these are going to notice. They're going to get, so that's where the maximum is going to occur. It's going to occur around that hole. And so we just need to know what that is. And the other part of it is there's kind of this cool, complicated, well, it's not even really complicated, but it's just a little bit time consuming. Take a look at what's kind of right below this. So this is straight out of your book. I just copied it onto your note sheet, but notice it says to get this K value, notice this one's a fillet. To get this K value, to read it off the chart over here on the left, notice we've got to take R and divide by H. What's R and H? Well, I don't have to memorize that. Notice R is the radius of that fillet up there, and H is sort of the thickness of that small section, not the big one, not W, but that small section. If I divide those two measurements by each other, then I can look in this table. Well, where do I look? Notice all the different lines. And so notice then there's a W over H number too. W over H, like what are all, there's a whole bunch of W's over H's. What the heck is W over H? Oh, it's the width of the taller part of that cross section. That's not really cross section. Taller width of that side versus kind of the shorter one. What's the transition? It's like, what's the ratio? So this 4 would mean, oh, it's 4 times taller than it is, down in this section over here. And so you look at those two numbers and then that kind of reads a K value off of it. Now you kind of know what to multiply the normal, what the normal stress would have been. So it's not, once you get the hang of it, this isn't that hard to do. And the same thing is true with a hole. That's just kind of a different formula. Notice for that one, there's only one graph and all you need to do is figure out what 2R over W is. And then I look over at this, what's 2R? Oh, that's the diameter of that hole. 2R is the diameter of the hole. And OW is the kind of the height of that piece. And so if I divide those two things, then I get a number and I look this up in the table and it's like, oh, 0.3. Oh, look at that over there. Oh, I see it's like 2.3. 2.3 is my K value. And so let's play with that. Let's see if we can figure this out. Let's see, a second ago, that hole looked simpler to me. I don't know if it looks simpler to you, but let's just play with this a little bit. So notice in this case, the main formula that we saw on the note sheet a second ago was that K was the new, before we always just calculated sigma, and they called it sigma average in that formula, but I'm just going to call it sigma because that was just the stress we always calculated. And so that was kind of our formula, and K was the ratio between the maximum caused by these stress concentration points. So that's kind of my basic formula. And so notice they told us that the sigma allowable here was 21 KSI. So that's kind of a hefty number. Where does that go? Is that sigma max or is that just sigma? It's talking about the material. Notice it didn't tell us it's aluminum or whatever it is. They just said, hey, the maximum amount that aluminum can handle. Notice they said it's allowable. Where does that go? Do you think? It's okay to be wrong. Yeah, you're exactly right. Again, I find myself wimping out as I've told you, KSI. Let's see, that's 1,000 PSI. Oh, so it's 21,000 PSI, pounds per square inch. I can write PSI, but remember, I'm looking at the units. I want them to cancel. And so okay, cool. So that's the allowable amount. And then they say, okay, well, then let's not pull too hard on it. I mean, that kind of makes sense, right? If that's the allowable amount that this metal can have, and then someone's went and drilled a bunch of holes in it or something, then the question is, well, how hard can you pull on it without breaking it then, right? And that kind of makes sense why an engineer would want to know that. So does it make sense? I got a formula now, but it's got two unknowns. It's got K and sigma, and I don't know what either of those are. And then it's asking for P, which isn't even in the formula, right? So that's kind of a little bit frustrating. Like P is not even in there. But remember, sigma is equal to P divided by the area, right? Or, I mean, we use the N, so it's the normal force divided by the area. So the normal force divided by the area. So it kind of is in there if we were to replace that. And so that's kind of interesting. Let's think about that. Well, notice they said in this particular problem is kind of hard because it has a fillet and a hole. In other words, which one's going to cut, where is it going to break? Is it going to break, if you will, over here, thanks to that fillet? Is that where it's going to break? Or is it going to break over here thanks to that hole? And we're not really sure. So we're basically going to find the P for each one of them and just kind of see which one is the limiting factor. And maybe this isn't drawn to scale, so we're not really sure. At a glance, I would say, well, let's see, the leftover material there is that tall. And then if I look at the leftover material here, frankly, they look about the same, don't they? So it kind of feels like this is going to be tough. It's going to be a tight race. But maybe the way they concentrate around those shapes is different. I don't know. My gut reaction is should be about the same. Not really sure where they're going to break. So let's do, I don't know, let's do the fillet first, I guess. Fillet. Differently so I can write legibly. So let's see, we'll go back there in just a second. Be kind of nice if I had that note right here so we could look at both shapes at the same time. If you have this in front of you, then when I switch to the other page, you'll be able to recognize it. But I remember it was asking for, I think R over D, was it? Was it W over D or no? What is it? R over H. And W over H, that was it, wasn't it?
Yes.
There we go. So I got to figure out what those two things are. Well, R was the radius of the fillet, and I can see here that that's 0.25 inches. And then the height was this. Yeah, and notice, get used to dimensioning things. Notice they didn't feel like they had room, and so they kind of put an arrow here and an arrow over here, and they're saying it's 1.25 inches between those. What do you notice about the units of that? What happens to them? Yeah, they go away. So that's kind of interesting, isn't it? So if I divide those two things, I guess I didn't write this down, so now I'm going to have to calculate it. So you tell me what that is and you bring a calculator. Got my phone. 0.2. And if I take the width, which is 1.875 inches, and divide by H, which is still 1.25 inches, what do I get for that? 1.5. So that's what I need to look up in the table. So let's go see if we can figure out what K is looking at that table, 0.2 and 1.25. So for the whole fillet, sorry. Whoa, easy. Slow down, partner. Relax. Don't get excited. 0.2. So R over H was 0.2. So I'm definitely, somewhere on this line. And then we said we were looking at the 1.5. Is that right? This one? And that's this one right here. So I'm looking right there. Do you agree with that? So this would be 1.7. So it's a hair above 1.7. For you mathematicians, you might be a little troubled by like, really, we got to look this up in a table. That just seems kind of weird. Like, isn't there some e to the x formula that would model that? Or, maybe this is just made so people don't have to suffer and know a bunch of algebra so they can look this up in a table. Turns out the overall gist of this is it's pretty darn complicated. I plugged some points in, I think, for this graph down here, and I asked Desmos to try to find the equation that modeled this, and it didn't want to find it very well. Like, it almost made me wonder, and your book references this, but it made me wonder if this was almost statistically determined, like they just took measurements on something and plotted the points, and there actually isn't a simple equation that works. But I don't know, what do you want to call that? 1.72? Doesn't matter. Recognize it's above 1.7. Who cares what you call it after that? I'll call it 1.72. So this produced K is 1.72. So that's kind of an important number. And so now I'm ready to roll, because then I can go back to my kind of that top equation and say, okay, 1.72 equals 21,000. And notice that's unitless. That K is unitless. It's a constant. It's a multiplier, so it isn't going to change our units here. And if you think about it, that makes sense, because this was PSI, which is sigma, and isn't the bottom sigma too? Like, isn't it PSI over PSI? So wouldn't those just cancel? Yeah, that's right. So you can either calculate this number right here by dividing 21,000 by 1.72 and kind of writing that number down, or you could say, hey, I already know that this number is, the area. And I want you to watch this carefully. And this is on the note sheet. I didn't say this, but like, what area are you going to divide by? Let's think about that for just a second. Does it make sense on this right here? Don't I have like that cross-sectional area right there? But then don't I also have this cross-sectional area up here? So the question is, like, which one is it? Do you see what I mean? Like, because it's got two of them now. All the time we've ever done this before, it only had one of them, right? So which one is it? Well, it's the weaker of the two. Notice they actually gave us the formula right there on the sheet. It's like, take that N, that normal force, and divide by what? H times T. Oh, there's H right there. That's the height. and there's T right there. Oh, they're basically just saying, use the smaller one. That kind of makes sense because that's going to be the weak point, right? Because whatever force you put on it, that little square is going to have to carry it. Over here, it's kind of easy. Like you got a much bigger area up there, so no problem. It's not going to break there. It's going to break in the weakest point. So do you see why that's kind of logical that that'd be the weakest spot? So in our problem, I could just find sigma right now and then recognize that sigma is equal to n over that area, or I could just go replace it right now if I wanted to. Maybe I'll take that approach. If I replaced this with n, I guess I'll write p. No, I can't do it. I'm gonna write n up here. P just bugs me. Like, what is that supposed to stand for? It doesn't stand for anything. And the area on the bottom is, well, how tall was this thing? 1.25 inches. And we said it was 0.125 inches, wasn't it? 125 inches and its width. So isn't that the area of the rectangle that's over there? You okay with that? So I could do that right now if I want. And notice n would be pounds and inches times inches on the bottom would be square inches. So that is a PSI number down there, even though I didn't write it out. If all goes well, you get n as 1,908 pounds. So do you understand? It's kind of like, well, don't pull more than 908 pounds on that or it breaks. Now, the question is, if we kept it at 1900, then would it not break? Well, we don't know what's happening at the hole yet, right? 1900 could break at the hole. So we're not really sure if this is the right answer yet, but if all there was a fillet, it'd be the right answer. So now you as an engineer can place a limit on it and say, okay, don't go over this and you're fine, right? How are we doing? Going too fast? Makes sense?
How do you know to do the fillet first?
No, it doesn't matter. I just doing them both. Just picked it randomly. Let's see. So I need a K value for the hole. So the hole says, awesome. All you need is 2R over W. Remember, the 2R was effectively the diameter of the hole divided by the total width. And again, that kind of makes sense if you think about it, because we're finding a ratio of sort of how much material is left, right? So the diameter divided by the width, 2R over W. And then I'll look that up in the table. So let's see if we can pull that off. So 2R over W, let's see, 2R in this case. Well, notice they gave me the diameter. It's 0.75, so that is the diameter. I'm not doubling that. So 0.75 inches. And then the width is 1.875 inches that we used earlier. Somebody blurt out what that's equal to. For some reason I didn't write that down.
0.4.
Sorry?
0.4.
0.4. So there's the number we're going to use in the table. And then the table will tell us what K is. And so what is K? 0.4. That was nice. Notice they put some thought into this. It's kind of cool. It didn't come out like 0.372 or something weird like that. I noticed when I was making the review for this that like, that's no joke. Like I made it up randomly and it came out weird every time. It's really, wow, something got to work hard at this. Not that you can't estimate it, but okay. So 0.4, awesome. Where's it hit? Right there. And so, you know, you could say, well, that's a hair under, you know, I think I'll call it, you know, just a hair under 2.2. If you were going to make a mistake here, would you be better to round that up or round it down?
Yeah.
Actually, I'm not sure. I got to think about that really quick. If I round it up, that's going to make it safer or worse.
So the K stands for concentration.
Because in the end, so I'm going to call it 2.2, but if you look closely, it's actually a little under that, right? So for whatever reason, I'm going to call it 2.2. Let's just go back to the other page though and stare at that equation for a second. So this equation here, if I make,
It'll actually make it worse. You should estimate it though, because it's going to be able to denominator.
so does it make sense because I'm going to multiply this let's see, I'm gonna multiply this over to the side. If K gets bigger, then does it make sense it's gonna make that maximum get bigger? So I think if I make K bigger, then I'm making the max bigger, which is not
Yeah.
necessarily good. Is that right? Seems simple. I'm sort of fumbling with that. I don't want K max, I don't want sigma max to be bigger, do I? Yeah, whatever. As far as the test is concerned, you know, you're going to pick it off there and get fairly close. And so now I'm in the same spot I was. And I say, okay, cool. That means 2.2 K, just like last time. So I'm doing the same thing I just did over here, is 21,000. I'll leave the units off this time because I know it's PSI. And then divided by, well, sigma again. But what's sigma over there? What do you think sigma over here is going to be? Over here, we said it was like that area. What do you think it's going to be over here? It's going to be there. Well, just like last time, it's worst case scenario. Where's the worst place you could put it? Right here. Does that make sense? Now, if you did that, it would be kind of like top and bottom. So that I need the total height of that, which I guess would be this red height kind of minus that diameter, right? And that'd be how tall it is. And then it's the same thickness as before. But again, I'm showing you that just based on logic, because notice what's sitting right here. It tells us right there that that's how you find it. Let's stare at it a little bit. Well, remember sigma was n divided by an area. We'll stare at that area formula. Again, when I first looked at this, I just was doing what it said to do. And I didn't realize, oh, that totally makes sense. If you take width right here minus the diameter, isn't that distance right there? Isn't that combined with minus 2r? And then if you multiply it by how thick it is, it's like that's what's left over. It's actually the same exact logic. You're just taking the smallest place and saying that's the weakest place, and you're saying that's what you got to work with. That makes total sense, doesn't it? So this was width minus 2r times t. And that was just the area, right? And so it was n divided by that. So if I come in here and say, well, my width was 1.875, my 2r completely was 0.75, and my thickness, wasn't that 0.125? Yeah, 0.125. Then I can solve for n. And if I don't screw that up, I get n is 1,342 pounds. Notice, contradicting what I said earlier, those are pretty far apart. I mean, actually, the blue one is like 50% more. So they're not actually quite the same, which I'm a little surprised at. Maybe, again, I'm not really sure why. I didn't think about it till I was just discussing it with you guys, but maybe they just didn't draw the drawing to scale. When I'm looking at the drawing, I'm not sure. But the question is, which one's the right answer? Why do you say that?
That means if the top one, if we apply the top force, the bottom one will snap.
Perfect. Couldn't be said any better than that. If I applied that top force, then it's going to snap at the hole, right? So I've got to pick the limiting factor here. Got to choose the lesser.
Now, if you round it down to 2.1, it would actually make.
Yeah, there's the answer to our question, what you just said. If you round down to 2.1, what does that do for that number?
So you got always round
It
up.
made it bigger. So the fact that, so if you, when in doubt, round up, that means I just put a smaller number there, because I'm sort of putting a sign on it, just like you see bridges on old roads. It's like weight limit, this much weight. I'm putting a limit on this and saying 1,342 pounds is the limit. So good job.
Oh, no, I'm sorry, I meant the K value.
Yeah.
Okay, cool.
So you meant round, the fact that I kind of rounded the K value up was a good idea, sort of by accident, right? Because I wasn't able to like figure it out in my brain. But you tried, good for you, 2.1, and came out more than 1342. So the fact that we're looking for the smallest value here to make sure we don't break anything So now we realize the holes where it's going to break if you overload it, which is kind of cool that you can actually predict that. And so I don't have to worry about the fillet.
We just round up to the nearest 2.2.
I just looked at it and got lazy. In my case, I was like, oh, it's pretty close to 2.2. I really didn't think about it. I wasn't until we just reasoned about it together. I didn't even really consider it. I did 2.2 when I just did the problem myself. But now that kind of makes sense. And as far as your test, I mean, I don't care, like, because you're going to get decimals and, it'll be a little bit messy. And as long as you're close, you're reading everything fine. It's okay. So that's kind of cool because that's not that uncommon. And so this idea of a stress concentration is real important. Incidentally, have you noticed anytime people pour concrete that's never just like a giant flat concrete? The sidewalk right out here, they've got lines cut in it every like foot, 2 feet, just lines everywhere cut through it. The rule of thumb in concrete is don't go more than 10 feet without putting a line in the concrete. Now, why do you do that? You're basically taking concrete that used to be 3 inches and you're saying, hey, right here, it's going to be 2.5 inches. Well, when the ground moves and cracks, where do you think it's going to crack? In that weakest spot, because that's exactly what we just drew. It's like the concrete's cruising along and then suddenly, warm, it necks down, and instead of being 3 inches thick, all of a sudden it's 2. What's that going to do? It's going to take whatever force is in it and concentrate it right there so that it breaks right there. Well, what happens when it breaks right there? Well, it's down in a hole and you can't see it. So next time you go, and it's like it makes it, and have you seen concrete crack where you get this wrong? Because it cracks like lightning. It's like goes all different directions and it looks really terrible. So next time you walk out on concrete, like go look in the crack, look in that little depression and you'll see it's cracked there. But it looks good. It's like you made it crack straight because you created a weakness in it. It's a huge part of the way engineers work. In an engine, if you over torque something, when I first worked construction, I drove this flail mower, which is on the back of a tractor, and it has power that comes off the back of the tractor. And as the tractor drives, the motor spinning. Well, what happens when I hit a rock? Well, that's tied clear back to the motor. And there's a lot of stuff that could break. Does that make sense? If something is spinning really fast and you suddenly say, stop. Well, what I want to break is something cheap. Does that make sense? And so there was this teeny little bolt on the outside of the motor that was a part of the connection. So it was like this female pipe and this male pipe, and then there was a cotter pin kind of sticking through it. It wasn't a cotter pin, it was like a bolt sticking through it, and that was designed in to be the weakest link. So if it hits something, it would shear that bolt off. 20 cents. I have like 3 of them in my pocket when I'm driving that thing. Just go out there, line it back up, put another thing in, whoop, take off again. Motor's not broke, tractor's not broke. I mean, that's ingenious, isn't it? I mean, who thinks of these things? But that's exactly what we're talking about here. It's like it's a weakness. And so this is cool stuff. This is really practical stuff.
I feel like my brain will never work that way. It's just gonna be someone else's job to create those like genius ideas. And I'll
Yeah.
be like, great job, man. Well, I'll implement that where I am.
Yeah, well, that is what it's going to be. I mean, people have thought about this stuff for 100 years. And so, you'll be working on something and it'll be more like somebody has the great idea to design a weakness into it. And you'll just be up to you to decide what kind of material is that little bolt going to be and what diameter do I pick? Because practically speaking, if it breaks because you got into some tall grass, that might get a little old, right? Like it broke too easy. But if it didn't break when you hit a rock or something, that's not so good. And so, it's like the idea that I would sit there and make a bunch of calculations about how fast it's spinning in RPMs and it hits something. And, what force does that transfer back here? I mean, you can sort of see that it's like, we can kind of figure that out now. Isn't that kind of cool? I mean, I don't think it'd be easy, right? Don't you, if I gave you a tractor and said, all right, take a bunch of measurements, and don't you feel like that'd be hard? But can you see we're there? We're doing that now. We're right there. This is pretty exciting, I think. So to that end, let's take a look at, I don't think we'll do this other problem, but I just want you to look at it really quick, just so you kind of see the difference. Notice what this question is asking. It's the same exact drawing. It's just saying, well, what if you knew how much force you're going to put on it? So let's pull 2,000 pounds.
If it's the same diameter and everything, wouldn't we just look through the hole?
Yeah, now that we just learned that the hole is the weak point, does it make sense we could maybe look at this a little bit differently. The maximum stress is going to happen. Remember, stress is the force divided by the area effectively with this K value, this concentration value, this multiplier, because notice we just said a second ago was it 2.2? That's a 120% increase. That was a massive change. That wasn't just a tiny little increase, it was massive. So we're basically just multiplying it by something to make it larger. So this would be the same problem. It's just that instead of not knowing what N was, we're not going to know what the top was, right? A second ago, we had K equals sigma max over just kind of ordinary sigma. It says this time we're actually going to know this one. We're going to have a number for this one. We're going to look at the table. We're going to have a number for that one. And then we're going to be able to solve for sigma max. And that's what it's asking. What's the maximum stress? Notice it didn't say force, it says stress, like it's sigma. We're done. If we can figure out what sigma on the bottom is as a number and K is as a number, we got it. And so we'll know how much stress is there. Now, why would you do it that way? Well, this is probably a little more realistic because here's this weird part, and because you do all these calculations in the tractor that it's going to end up with 2,000 pounds of pull on it. You don't get to fix that, right? You're just stuck with that because of the motor. So then it's like, okay, well, how strong does that need to be? Should we use aluminum? Oh no, that'll snap off. Aluminum's PSI strength. Remember, you can look that up in the back. The PSI capability of aluminum might not be good enough. And so, we're going to need structural steel. Or we might say, well, you're going to have to, fix this. 0.125 inches is too thin. Let's take it out to 1/4 of an inch, and then there'll be more material, and then you could use aluminum or something like that. You might have to change the design of it a little bit realistically to make that happen. So I think this is actually a little bit more realistic of a question. So let's see, I think I will stop recording.